All right, so it's my pleasure to introduce today's speaker for our research seminar series for the Integrative Movement Sciences Institute. Greg is a professor at Georgia Tech with joint appointments in mechanical engineering and biological sciences. He currently also serves as the interim executive director for Georgia Tech's Institute for Robotics and Intelligent Machines, and he directs the Physiology of Wearable Robotics Lab. And he's a senior research scientist at the Institute for Human and Machine Cognition, so keeps very busy, I'm sure. His educational background reflects his interdisciplinary research perspective. So he did his bachelor's and master's degrees in mechanical engineering. Then he did his PhD at University of Michigan in kinesiology and mechanical engineering, so joint PhDs. Then he followed that up with a postdoc fellowship, NIH funded, at Brown with Tom Roberts in integrative biology. We go way back because we met back in Ann Arbor during the Michigan years. And so it's great to have him part of our collaborative center, the Integrative Movement Sciences Institute, and be able to work together more often. So one of the things I just want to say that really stands out about Greg's research is that he's designing devices, but he takes a very principled scientific approach to using biomechanics and physiological principles in designing these assistive devices and figuring out how to make effective use of them. So I'm sure we'll hear more about that today. And so please give him a warm welcome.
Thanks, Monica. Great to be in Irvine. I got a surfing lesson yesterday from Manny Azizi. I'll let him decide whether it was a success, but I got up on my feet a few times and I didn't die. So I might go again in a couple days. It's really great to be here. And I just want to commend Monica and the leadership team who built this institute that I think our community's been dreaming about for a long time. And Monica really, took the reins, and now we have this great collaborative thing that lets us come to each other's towns. And it's happening more often, and it's awesome. And so hopefully NSF hears me and they will continue the funding for the center. Okay, I'm gonna get right into it. So this used to be a slide about Iron Man, the movie. Now it is not, right? We have wearable robots that are out there. And they're in popular media, but they're also really being used like in factories and now for recreation. They've been in clinics for a long time, and they're getting better and better all the time. What's really cool though now is I feel reasonably comfortable saying that they're products, right? There's a pipeline now where we're all going to be able to buy these and maybe make them part of our everyday lives. Some examples of the companies that are in the game are Biomodem. They've been in the cerebral palsy rehab arena for a while. This is Zach Lerner, founded the company, and Ray Browning now runs this company. Defy is an MIT spinout that's now joined with Nike, and they're working on all kinds of applications. And then Skip is a knee device that came from Google Moonshot and is now a company. And then the Hypershell, we actually have a couple of these in our lab. You can buy these for $1,000. They're still not cheap. But if you're used to paying that for your skis and your ski boots, maybe this is an entry-level exoskeleton that you'd be willing to try. Okay, so they're here. And I still think there are a number of open challenges, right? So I used to call the open challenges and put them in quadrants. First two quadrants are the form factor. My title alludes to the idea that we want these to be clothing eventually, right? So what that means is we need softer form factors, and we need more sort of biological inspiration in how we arrange the actuators and the sensors and so forth so that they can be wearable. And that also involves making actuators that are not, standard AC motors that might be large and have a lot of mass and lots of transmission backlash and so forth. So these two areas, I think we've made good progress in. Here's an example of an exosuit, not quite clothing yet. That's a hip knee device. It has like combinations of carbon fiber and other soft elastomers and materials that make it quite wearable. And it's also quite powerful. So it can produce about 30 to 50% of your normal mechanical output at those two joints. And then there's also kind of this revolution now in knitting and textiles, which we've gotten a little bit involved in. I won't talk too much about our work there. We're certainly not leading. There's folks at Rice University that are really leading the charge here. And Krishma Singhal was a postdoc and is now at Rice that is doing some of that work. And the idea here is that we can like principally program textiles to have material properties that we would like to have on our bodies. And then, of course, that's a lot more like clothing. So I think we're doing pretty well in these two areas. I would argue that the frontier now is in sensing and control. That's always been a problem, but now it's more front and center because we have products. We even have things that are looking more like clothing. But I would argue we don't know where to put the sensors and what to do with the sensing information and how to control it. So a lot of what I'll talk about today in the back half of the talk thinks about control and sensing. So put a pin in that and we'll get to it later. Here's a little bit of the philosophy on how we run the lab. Monica already kind of mentioned this, but we're all about trying to understand the biological system first. We like simple models. This is a simple model we've got a lot of leverage out of. It's basically a hopping in place body in gravity, and we drive it with whatever the best muscle model of the day is. Like arguably still, we're stuck in hill-type model mode. We would like those models to be better. Not going to talk about that today, but that's a major focus of the IMSI Center. But the idea here is that even with these really simple models, a single muscle, a body that doesn't have joints, we can learn a lot about what that muscle should do under certain conditions to perform well. And then our version of the exoskeleton is just to put what we would call a force or a work source in parallel with a muscle. That's basically what an exoskeleton is. It's a parallel body that produces force. And then that question mark is like, what do we do control-wise in that green element to make it play well with the biology? And so we try stuff, we fail, and we iterate. And that's been the approach. More and more, we're trying to integrate modeling and simulation to make good guesses at what the green element should do. But really, it's an iterative process. We also take kind of a broad approach across scale. Most of what I'm going to talk about today is whole body human experiments, where we're either on a treadmill or we're on a fancy treadmill where we try to knock people over. But we do also do work all the way down into sort of tissue level. Lately, we've been trying to explore like sensory feedback in these kinds of preparations where the animal we can record from the animal's spinal cord. Okay, so I'm gonna start and go back to the archival stuff a little bit for folks that might not be familiar with that. And the topic's going to be economy. So the goal here is to build a device that can improve the gas mileage of locomotion, reduce effort, but as measured by oxygen, right? It could also be mechanical or neural effort. And this is kind of an aged review paper now because the data probably go down and to the right into the floor at this point. But and actually, Dave Rankensmeyer, who's in the room, asked us to write a review in 2020. Hey, like, where are we in the field in terms of improving gas mileage? And at that point, like, what's really cool about this is there's a steady trickle to the bottom right, which is time moving and performance getting better. And at that time, we could get 20% improvement in gas mileage, which is a big deal, right? That is like a 10% improvement is basically like a 10 kilogram backpack. Another way to think about it is if you walked around with your hands crossed all day, that would be a 10% penalty. So 20% is really high. It's hard to do that on machines that are truly autonomous and wearable. A lot of these data come from tethered machines that are in a lab and have big motors. And we're at 50% reduction now. This is the best result in the field from a multi-joint exo that's plugged into the wall with big cables. And that's coming out of Stanford's group, Steve Collins' group. So I don't want to say it's a solved problem. We know how to do that. We know when to turn the exo on. Again, how do you get that into a wearable form factor, right? That's light enough and people will actually pick up and wear is the next question. So like, where does our work fit in here? We took a different challenge at that time, which was like, we're going to try to do this, but we're not allowed to have any motors. So the challenge was, and we were thinking in an applied sense a little bit, because we wanted to try and see how good we could do without having a lot of added mass on the body, hoping that if we could do pretty well, people would pick that thing up and use it. And so I'll tell you a little bit about that. It's a quick story, but I think it's important underpinning. And it starts with the basic locomotion mechanics. So we think of like locomotion mechanics as a roadmap where we can create like analogy sort of design, right? So if I think about mechanical elements like springs and dampers and motors, there are analyses that you can do, inverse dynamics. People in this room have heard about that. That lets you say whether or not the action, the mechanical action at a given joint looks more like a motor, spring, or damper, okay? This is not new to the field. We kind of morphed it into a joint level approach because you put exoskeletons on joints. But the idea of motor, spring, brake's been around for a long time, right? And what you do is you put, this example is going to come from increasing the treadmill grade, but you can do this with speed or change the gait. You collect motion capture data and you put people on an instrumented treadmill and you run Newton-Euler physics backwards and you figure out what are the moments and power outputs of each joint. And you get data out that look like these. So on the x-axis here is grade, zero is level. Over here, the treadmill's up, you're going uphill. Over here, treadmill's going down. Color coding is, here's what the ankle, knee, and hip are doing. So just to calibrate you here, let's go over here first. At a steep uphill grade, relatively steep, the ankle produces a lot of positive work. That means it's like a motor. The knee is just tipping into positive work mode, but it takes a really steep incline to get it there. And the hip is really your power source. It's a motor. So if you think about that analogy motor, maybe that means I should put motors at the hip if I'm going to build an exoskeleton. How do I apply this thinking to the knee, which is the sort of superstar damper? As you go down, the knee modulates to become more and more of an absorptive element. You could also charge a battery with that if you like. That would be regenerative braking. But you can see here that the ankle, interestingly, never gets into damper mode. And then the ankle, which is always our favorite, because it's really involved in propulsion. It also has what I think is kind of fun morphology, right? There's a big tendon there, so we're interested in it from a basic science standpoint. But if you'll note, like at zero, it's a spring. Like if it's net neutral energy, that thing is storing and then returning, and it's not generating or absorbing net over a gait cycle. So the analogy there is spring. It screams spring, right? And never really goes into damping mode. Maybe starts adding to the motoring uphill. So if you're gonna, our idea here was if you're gonna build an exo for level ground and you don't want a motor, what should you do? We said, well, let's focus on level ground walking and try to use a spring. Okay, so we got that, put a pin in that. You can do a little bit deeper physiology and try to understand where that springy behavior comes from. And this involves ultrasound imaging. So that little yellowed out probe up there is an ultrasound probe. It's like about the size of a pack of gum. And it takes an image that is 60 or 70 millimeters long. And it can go quite deep, like all the way from your calf to your tibia. And you get an image that looks like that in cross section. And the red arrow is a tracking algorithm, in this case, a person hand tracking at that time, what looks like a fascicle. Okay, and the fascicles have pennation and length that you can track. You put that back in your inverse dynamics, you can start to separate out how much of the ankle joint work is coming from elastic return, elastic elements, or muscle. And these are the kinds of experiments that we see done with sonomicrometry and tendon buckles, like in vivo in animals, which are not possible in humans, right? So you have to take a non-invasive imaging approach to do these kinds of things in humans, and that's ultrasound is our friend there. Okay, so what you see here is speed going from left to right, and at 2, I have walking fast and running slow. So this vertical line is a transition from walk to run. And the bars are color-coded so that SEE, think Achilles tendon, that's the series elastic element, is that part of the bar. And then the fascicles are the muscle part of the muscle tendon unit. Note here, at 1.25, walking, which is near where you would select naturally, you're getting half of the positive work coming from tendon recoil, and that leaves only half for the muscle. So that's great for economy. Muscles really don't like to shorten fast. It costs a lot of metabolic energy. The system's leveraging the springiness there in order to save energy and other things, right? There may be other benefits of that spring. In running, it's even more pronounced. 3.25 is like, what is that, an 8-minute mile or something like that? It's not like marathon speed, but you're at 70% in terms of the positive work that's coming out of your ankles. A lot of that's coming from elastic recoil. And the muscle is left to perform this action, which is just hold so that the tendon can stretch a lot and then recoil. And so we think about that as a clutch. The mechanical analogy to that is clutch. So now we have spring at the ankle, and let's try to be bio-inspired by and put a clutch there. Both of those, if designed well, require no battery or external power, is what we were thinking. And so along comes Bruce Wiggin, and Steve Collins was a big part of the design process here. We collected these data at NC State many years ago now. But I just want to point out that, right, like that basic science that I just showed is converted into a clutch and a spring, which is just literally a door, like a porch door spring that's worn on the back of a carbon fiber, very, very paper thin carbon fiber brace. And the clutch is designed really nicely. It's a ratchet pawl that it has a kinematic constraint, which says when you bring your toe towards your shin just before you're about to strike the ground, the ratchet and pawl engage, and only one direction of free motion is allowed. You're allowed to put your foot on the ground flat, but you can't plantar flex anymore. So you get a free foot flat, and then as your shank rolls over your flat foot, that transmission is locked, and your body can transfer energy to the spring, just like your body's transferring energy to your Achilles tendon. But there's no muscle spending energy to hold it in place, because that piece of metal with the latch is holding. And so then the question is like, can you get a real benefit from that? And the answer is, well, this just shows the dynamics. Up here is the amount of torque that's being supported by the exoskeleton spring. So you can tune the stiffness of that spring. This is relatively compliant all the way up to pretty stiff. So I can get more and more torque support. And I start changing my range of motion a bit, right? So there's a trade-off here. If I made this infinitely stiff, ankle joint would lock up. There wouldn't really be any motion. Not good. You'd stumble around. So we're looking for, like, what is the best way to tune the spring in terms of its energy cost. And what we found was pretty cool, was that, number one, just by donning the paper-thin carbon fiber, we didn't see an added mass penalty that was statistically significant. What was interesting here is some people were getting lower calf muscle activation just to wear the brace. We think because we were partly stabilizing their frontal plane. And the added mass was not significant enough to cause a penalty, which you then have to cancel. And then we found that an intermediate spring was the best for reducing cost. And I'll get into sort of why that happens at a muscle level in a little bit later. But the news here is, like, if you could make that thing, wearable, certainly you saw that thing. It's not. It has this huge moment arm that juts out of the back. Can't walk up and down stairs with that. You can't change the spring stiffness on demand. The clutch is exquisitely tuned to that walking speed on a treadmill. So, like, all that to say, it's entirely impractical. But engineers could go to work and try to make the impractical things better, right? Was the idea. Okay. Then we said, we don't want to build any more porch spring carbon fiber devices for each individual. Let's try to turn this into, this is called an emulator system, also inspired by work from Stanford and also at Harvard in Connor Walsh's lab. But the idea here is, let's just put a motor that's cable driven and attach it to a cable drive, and then program a computer to feel like the spring, which means now we have spring stiffness at our fingertips. We can say, oh, Manny needs this one, Monica needs this one, Dave needs that one. And that lets us be very quick and do high throughput experiments where we can optimize. And so Rich Knuckles, when he was in the lab, checked this device across multiple speeds. Another surprising and interesting, and still we don't understand fully the mechanism. We got good results at slow and fast walking speed. You can see there we recovered the small benefit of having a spring at intermediate stiffness, but at 1.5, we could not. There was no spring that reduced energy cost. I'll get into this a little bit later too, but we think it's a trade-off between length, tension, and force velocity dynamics of the muscle underneath the hood. But really, there needs to be a lot more careful studies. So we went deep again. We're now going down. We're peeling layers of physiology. We're looking under the skin. This time we're tracking the soleus muscle, which is the uniarticular muscle that we're trying to mimic. And so that's what that yellow line is. And the reason we're doing this is because we want to see, like, when the device is now on there, what does it in turn do to that tuned clutch-like behavior that existed before we put the device on? We don't want to disrupt something that was already working well. And what you find is, this is just an estimate of the muscle force of the soleus coming from inverse dynamics. We're making a lot of assumptions here about force sharing and other things. So it's a very rough estimate, but it makes sense. The forces are going down. And especially in late stance over here, which is the push-off part, you get a really large reduction in force, especially for the stiff springs. What was more interesting is where the muscle is using its length tension curve. So what I'm showing you here are traces of the yellow tracked soleus fascicle that you saw on the previous screen. This is what it looks like across a gait cycle. Right here is about where swing phase starts. The pink strip is where the force is maximal. And we're using that as a window to evaluate what the muscle's doing. What length and velocity is it using at the time of peak force? And first thing you can see here is that as I turn the stiffness up on the spring, I push muscles to longer operating lengths. And this is because the spring gets shorter, right? Like because there's less force on it. So springs just get shorter, muscles get longer if all else is the same. You're moving with the same kinematics. It's got to be taken up by muscle plus spring. Spring gets shorter, muscle must get longer. And that's what we see. The shape of those curves tell you more about where you're on the force velocity relationship. Won't dive too deep into that. But point here is I've got lower force demand because the spring is there. And I can operate at longer lengths, which means I need less muscle oomph to get that same force. So I have two things that are good coming from the exo. If you want to map that onto your length tension curve, this is just we did not measure length tension curves for all these people. This is like from a textbook, right? It looks like a sarcomere level length tension curve, but it's just for demonstrating that what the exo is doing is going from this nominal point on the ascending limb and getting pushed rightward to longer lengths where we know that you can produce more force for the same activation. And that means you can summarize that as increased force capacity. Force pre-inactivation is better. And that comes with also a reduced demand. So that's a win-win. And we think that that's what's responsible for the good behavior at low and intermediate stiffness. The story continues, but we don't have time to go deeply into it. Why is it bad at stiff springs? Your TA starts to turn on. Other muscles start to turn on. You can't control it. It's, the nervous system's like, what's going on here? And I also think that when the muscle gets long, it still wants to shorten to the same spot to get the swing, higher velocity. So at the really stiff springs, you have coactivation and very rapid shortening at the end of stance that kind of eliminate the effect of the length tension and reduced activation. Okay, so that's that story. So then you go into dreaming mode. Oh, like we can measure fascicle dynamics. Maybe we can build a device that can push the fascicle dynamics around. And if physiologists know where we want our muscles to be operating, like why don't we think about exoskeletons as machines that steer muscles in the loop, right? Great. Well, to do that, you'd have to get a real-time image, process it fast enough, right? Like we don't have the sensing is the bottom line. Fast forward to today, maybe you can use machine learning or something to learn the relationships between wearable sensors and the deep physiology. That's a direction we want to go. Then you can do things like, oh, I want to operate my tendon at higher strains over the next 6 months because I'm a long jumper and the athletic trainers and physiologists say I need stiff tendons to win the gold, right? That would be like pie in the sky. But from a rehab context, there might be other things that would be goals in terms of tissue properties, etc. We're not going to go into DOE-EM, sorry. So that got us, we wrote a review paper where we like review papers where you imagine things in the future. So you can go read about that if you want. We're not there yet because the engineering is keeping us from doing those muscle movements. Okay, so we're going to switch now to sort of aging. Okay, so how could a device like this that operates at the ankle help an older adult? And this is collaborative work with Jason Franz at UNC Chapel Hill, still kind of ongoing. We have some stuff we have some stones that are unturned. But here's the first thing to note is in aging, this is the stance phase. This is the net ankle joint moment. So think of it as like the sum of all the muscle forces to propel you. And in older adults, which are coded in gray here versus their young control counterparts, the peak moments, the peak forces you develop are lower. The dashed curve is power output plotted on the same axis. Lower forces, similar velocities give you a similar decrement in power, which is work, which something has to do to move you. So you have to recruit more muscle maybe, right? So what that leads to, also the other thing that happens is that your Achilles tendon gets more compliant. So you see a reduced capacity to push and create work using that clutch spring mechanism. And the tendons that you're operating are more compliant when you're old. It can be up to 40%. What does that mean? Again, back to our length tension curves. Your tendon determines where you go in this space. So if you have a more compliant tendon, you're going up this shallow slope. As you turn your force on, you have to follow the tendon's force displacement curve. It's mirrored in the muscle's length tension curve. It throws you left. That's bad. You don't want to be at short muscle lengths. And that means you have to turn on more muscle to get the same force. And then your cost of transport goes up. These are not our data, but there's classic literature that shows the cost of transport is higher by 50%. One interesting thing is that older adults they also self-select a slower speed, which is not for energy reasons, apparently, because their cost of transport minimum is at the same speed. If they were seeking energy minimum, even though they would be at a higher level on the red curves, they should still walk at the same speed, and they don't. Maybe they don't want to fall over. Put a pin in that. Our idea is, okay, you have a stiffer Achilles, a more compliant Achilles tendon. You have muscles that are not as force capacity driven. What can you do? One idea, and again, this is very underdeveloped, but it's an idea that we like, we're trying to get funding for, is to turn the exoskeleton into a resistance training device. So now, like, I don't want to have to deal with one of those clunky exoskeletons when I'm 60 years old in order to help me with propulsion. And I hate going to the gym. So why don't you give me some clothing that make it a little bit harder for me to push each time? So that's this idea. And what you would do is maybe like regulate heart rate or something. And you could have like a fancy controller that says, I want to dial in this heart rate, flip between assistance and resistance across speeds in a way to get me that workout, but also challenge me biomechanically. So, but I don't have anything to tell you here other than this is something that I think could be cool. And then you have to start saying, well, is it even possible? So normally I get the question like, you're going to put these things on people. They're going to be clothing. You decide to not wear it one day, but you've been wearing it for years. Then what? Like, is your body okay? Like, do you have this atrophy? Have you been in space on Earth for the last, right? And we don't have an answer because we don't have longitudinal studies yet that are long enough to address this. So I'm going to take you through a couple short studies that we did to try to think about it. One is a simple model, right? So that looks like the simple model that I had on slide 2. It's literally like a hill-type model that bounces a mass in place. But what was really creative about this project by Jordan Schroeder is she said, okay, we're going to have it hop for 200 cycles, and that's going to represent day one. And we're going to throw that model at another model, which says how much would the tendon remodel if its tissues were responding to strain. Okay. To anabolic or catabolic behavior. And then so basically, we did this game where we would have the model hop over a day, take some data from it, throw that data into your sleeping, and your tendon's going to remodel a little bit. Come back in day two, you've got a new tendon. Then the model's going to find the net energy best solution to that with that new tendon. It's going to hop like that for day two, and it goes for 200 days like that. And then there's 3 other rules that it had to follow. Under one condition, it's going to hop the same number of hops each day. That would be like, I always go to the grocery store and home, and that's it, right? Plausible. The other one is I give you an energy budget. So you get 10 Snickers bars tomorrow, and you're going to use all the energy that you got from eating them, and that's it. And then the third one is distance. So I'm going to cover a certain amount of ground independent of how many hops it takes, okay? And of course, like the energy minimum solution is telling me what frequency I'm using and sort of how much cumulative distance I cover in each hop. So those things are all subject to this closed loop remodeling. Okay, so here's what we found. Number one, like, don't be afraid. There are behavioral criteria in which you can actually gain tissue by wearing an exo. So we tried this on a bunch of different exoskeleton springs, all the rainbow colors that I showed you, right? We had models with each of those. And what I'm showing you here on this graph is a compilation of all the exoskeletons over all the days and how much the tendon strain changed due to those behaviors, and then how many cycles that model chose to take. And then the color code is whether or not the tissue grew in red, stayed about the same stiffness in green, or atrophied. And what you could see here is for the distance criterion, so it's bad news if you got to go to the same distance each day. What this says is that there are no exoskeleton springs that will keep you from losing tissue. But if you have an energy budget, you can find exoskeletons that will keep your tissue or allow it to actually grow. And of course, the gray one, so cycles and energy, news is okay. But for distance constraint, bad news, because you're not going to strain the tendon enough under that behavioral criterion. So how do you get out of that? Well, you can say, we're not going to constrain the cycles to be energy minimum. So now your app tells you how many cycles you need to go if you're only going to go a certain distance. And you can trade off the exoskeleton stiffness and the number of cycles that you go to make pretty much anything happen. So that's what this slide is showing. This is showing over the course of days for an exoskeleton that has no stiffness, if you just varied the number of cycles that you took, what the fate of your tendon stiffness would be. So you have a lot of control by the number of cycles you take. And our model, this is also subject to how we model the tendon remodeling. We said if the tendon sees more cycles, even if the strain is only just a little bit out into the anabolic zone, you'll grow more if you take more cycles at that strain. That's a key. We don't have really good experiments that verify this, okay? It's true for bone. We don't know if it's true for tendon. So what this says is even without the exo, I can dial in. This is kind of obvious, right? I can just do more steps and that I can make things happen. When I layer on the exo, I can do things more quickly if I get the right stiffness, right? But if I make things too stiff, up, game over. So there's also a sweet spot in terms of the remodeling. At least this model predicts it. And then this just shows if I were an engineer and I wanted to select hypertrophy, I would find the exoskeleton that gives me this. I would tell the person to take this many cycles with this exoskeleton that gives me that strain, right? So I don't know, it's a toy model, but at least it gives us some ground to say, hey, it's not all bad news if we can direct behavior while someone's in a device that's specified to their goal. Okay, so you're probably like, yeah, right, like that's a model. We really need the data from exos. We're saying the same things in the lab, but we're like, we don't have an exoskeleton. This is 5 years ago. We didn't have the commercially available devices. We don't have the exoskeleton that we need to do the experiment. Let's just play around with funky shoes. Maybe we can get people to wear strange shoes that make the dynamics at the muscle tendon level look like what it would look like for a spring-loaded device. And you can kind of do that by raising or lowering the toes. And I'm going to focus on the raised heels because these are in our society already. You know, not everybody likes to wear them, but maybe we should all get on board. Because raised heels have real benefits is what I'm going to show you, at least from a very small experiment that we tried. We couldn't get a lot of people to adhere to the protocol. I was in the raised toe group. It was total hell. I was on spring break with my kids trying to like hike up a mountain with the raised toes and counting my steps. And everybody thought I was silly, but it was cool. It was fun. I don't have a lot of time to get into sort of the mechanism here, but if you want to read about it, just type high heels plus muscle tendon morphology, and you'll find all these great papers by people like Neil Cronin and others who have showed that people who are habitual heel wearers have different muscle tendon units. They have stiffer tendons and shorter muscles. The question here was whether we could get people who don't wear heels to put on a funky shoe for 12 weeks, change their body, and then see whether we could get like a functional difference in their energy cost. Okay, so that's where we're headed over the next few slides. We got some people to comply with the heels, and they would take. We sort of found this natural split between users and non-users that was about 1,500 steps. And again, these are very sparse data. Like this is kind of pilot data for a grant. Came out as a short communication. So we really need to do the follow-up clinical trial of some sort to verify these things. But what we were able to show is that the gastrocnemius length got shorter for people who wore their heels, and their tendons got stiffer. These are from dynamometer measurements in each individual that we took pre-post. And this was the even cooler part. When we measured the cost of transport, actually, this is just at a single speed, so it's net metabolic rate at 1.25 meters per second. People who wore the heels, when they took them off and they just put their normal shoes on, had lower cost. So they were using their new body to save energy, is one way to think about that. So now I'll let you put your imagining cap on again. Oh, like if that were wearable clothing, and it might be possible to shape tissue loads over long times, like maybe you could have some performance goal that your wearable clothing lets you achieve, right? Still a lot more work there, but I like this sort of line of research, which is, and there's biologists in the room here, so that's really why I wanted to present this. And then the bigger picture idea is like, and I wrote a review paper with Massimo Sartori, who's actually doing a lot of the muscle level remodeling work now in his lab to verify that our models for remodeling are correct. We wrote this paper about, oh, if you could close the loop around these things and take control over tissue, like how would you do that? And I think, again, because now we have AI and other like data-driven tools, that this is going to become more and more viable in the next decade or so. Okay, so back to older adults. One way to help older adults is to give them funky shoes or smart clothing that is targeting tendon stiffness, for example. We're not there yet. Another way is just to check back down to our exoskeleton approach. And if you remember the story, they're kind of exact opposite stories. I told you that the exoskeleton makes muscles operate at longer lengths, good, and that older adults have more compliant tendons. And a side effect of that is that they have to operate at shorter lengths. So what if you go, boom, boom, slap those two things together and cancel them, right? Like, could it work to put the spring of the right stiffness on the older adult? Okay, so we tried this, but we also hedged our bet that maybe it wasn't going to be super cool. And we also had motors that people could wear that were getting to the point where they were powerful and light enough that motoring is really a viable option. We still had to check. So what we did is we took the Defy Exo boot, which is now the Nike device. We programmed it to behave like a spring. That's the pink curve. And then we also programmed it to behave like motors of low, medium, and high strength. And we matched the medium-sized motor to the peak torque that the spring would deliver, just to try to have a bit more apples to apples. And this was all just coding. We just made sure that those shapes came out in each step. And here's what we found. On the left, younger adults. On the right, older. This bar represents walking in the exoskeleton walking without the exoskeleton. This bar that you can't see is the control. It's walking with the exoskeleton motors off. The reason for this right here, a benefit of walking without the device, added mass. So put a pin in that, like even the Defies, now the Nike device, added mass penalty of 15, 20% just to carry that thing. They're fixing that, by the way. This is not a knock. We know how to fix this now. But the basic science question we want to know is, if you have a massless device, what's the best strategy? Should you operate it like a spring in pink, or a weak, medium, or strong motor? Across the two cohorts, the answer is motor. Motor for the win. We recovered the small benefit of springs for younger adults. We still don't know whether that stiffness is the right one for older, so we're not quite done there. But we put the same stiffness for young on old, penalty. And older got better benefits from stronger motors. And the strongest motor for old got you to a 25% opportunity, right? If you made that added mass cost zero. That's huge. And we know how to do it with motors now. So pains me to say it, but we need to move past the spring solutions for now and focus on really dialing in the motors. Then maybe when we have multi-joint suits, we'll place the motors on the hip, I'm going to argue, and we'll come back to springs at the ankle just to get a little bit more. But the reason for hips is this. This was very surprising. What I'm plotting here on the x-axis is the amount of savings in the biological ankle power from inverse dynamics. So I do inverse dynamics and I subtract the exos contribution. And I plot that against the change in the metabolic cost. So what this says is that as I reduce the biological ankle power, cost actually went up for these people. However, they were able to learn how to use their device to offload their hip. What this says right here is that as the hip power went down, so did the metabolic cost. And for those same individuals, they actually increased, right? There was the opposite effect local to where the exo was. So they're learning a new motor coordination strategy to take this thing on their ankle and torque less with their hips. Doesn't matter whether you're young or old. So, and it's like, well, why do we want to put all that distal mass there when we're just offloading the hip anyways? Let's just build some powered pants, right? Like some shorts. Let's focus on the hip. Okay, so we started doing that a little bit. This device is also tethered, so it's not, not available product, but we wanted to see if we could do some hybrid spring-loaded motoring, basically, some hybrid between springs and motor. And we did a complicated experiment where we varied the engagement angle of a virtual spring and how stiff it was. That's what you're seeing here on Y is where it engages. and on X of these contours is how stiff it is. Switch over here to the metabolic cost column right away. Blue is good, red is bad. And then we have slow, medium, and fast walking. So if you look for blue in the right column, that's where metabolic savings was. Intermediate speed, relatively low stiffness, intermediate engagement angle. And we could get a 10 or 15% reduction. So all this to say, like, hip's a viable option, even for devices that are hybrid spring motors. So that's cool. So what do we do with that? Next thing we wanted to try is, if you have a hip and an ankle operating together, don't care about energy costs. I just want to beat the light in the crosswalk. So I need to go fast, right? Like, don't want to get run over by the bus. So what we try to do then is dial in the shape of the hip and ankle torque patterns together to make overground walking faster. And the way that we're doing that is we just have a laser speed check. People start on a starting line. We ask them to walk as fast as they can, and we try to iteratively find the right shape of their torque at the ankle, and results TBD here. This is sort of just coming off the presses. But right, the point here is that it's not only about energy cost. Like, in the real world, I probably don't care that much if I can't cross the street without getting run over, right? And I also don't want to fall over, which we'll get to in the out slides here. Okay, so just to pause here, that was sort of the economy story for aging and younger adults. And I just want to say that I do think, like, now we have wearable sensing and AI, we can start to think about how we would make smart clothes to do things, because the technology is getting there. Still, I don't think we know what the technology should do. Okay, and so let's talk a little bit about balance now, right? So first, don't fall over. We've done a lot of work in the lab using different kinds of perturbations. I'm not going to have time to go into all this, but this one is our falling in the hole experiment, inspired by Monica's guinea fowl stuff from a while ago. We're like, oh, how do we do that in humans? Story there is have people bounce in place and then, like, pull a block from them. I'll play the video here. I probably won't be able to. You get the idea. Over here are slips. So we can have people on a treadmill belt, and then ice comes and they slip. We can do that at different times. The one I'm going to focus on today is platform slides. So over here, again, won't play the video. There'll be videos later. This is just you're standing in place and you get an unexpected pull of the rug from under you that pitches you forward. You can also pitch in any omnidirection, right? And you can do that on a treadmill, which I'll show you a little bit about in a bit. So now the question was, can you just improve standing balance with a device on your ankle that helps you put your center of pressure toward your toes fast? And the real question here was, like, well, maybe what we were thinking is maybe you can, because animals are slow, actually, right? You have to, like, hop mile in sheets and stuff like that. There's physiology that slows signaling down. And there's a time window of 150 or 200 milliseconds that people have before they can even turn on their muscles. But an exoskeleton doesn't have that. And so we cheated here. Full disclosure, this exoskeleton knew when the platform was going to move. But we fired it on the platform movement. That's in red. Call it artificially fast. Then we delayed it by a normal reflex latency. So that's physiological, right? If you were driving that exoskeleton with the person's own muscle activity, it would look like blue. So we don't really know how to make the exoskeleton all-knowing yet. Like, how does it detect the perturbation? But the point here is, if you could, we'd be able to improve balance. Here's what the experiment looks like. That's the exo off. Maybe able to tell a difference here. There's an earlier toe rise when the exo comes on. Sorry, I take it back. This one's physiologically delayed. This one's artificially fast. Yep. It's kind of like it's very hard to see. I mean, we're talking about milliseconds here, but you can I can see a postural difference. How do we measure balance? The game was this: if you take a step, you fell. So we gave them lots of different platform displacements and tried to zone in on where they would take a step 50% of the time. We can argue all day about whether that's the right measurement of balance. That's an open question, but this is how we chose to do it. And what we found is that with the artificially fast policy, people took 10% less steps. Or another way to think about it is they could handle a 10% larger 50% line on the amount of perturbation they could withstand before taking a step. Okay, so that's cool. This one's for the physiologists in the room. We had ultrasound and EMG, inverse dynamics, like all the measurements going. And we did an analysis to try to understand what was driving the soleus activity of the body. Was it a center of mass level thing? Like the EMG is more related to the center of mass mechanics. That's here in mustard color. Or was it more related to local variables like moments and velocities from ultrasound, which would be a proxy for like your proprioceptors? And what we found is like some evidence that this is a global controller, that the EMG that you see at the ankle is more related to what the center of mass was doing than what was happening locally at the joint. And that kind of inspired a whole new, this is work with Lena Ting and Kristen Jakubowski, both IMSI members, and Aaron Young. Like, what if we just use that as our control? Lena had developed this global center of mass feedback model over years, but never thought about applying it to exoskeleton control. Actually, I think she did. She didn't have a partner with an exo, right? So we're like, hey, we got an exo. And the idea here is just to estimate the center of mass mechanics. You can do that with wearable sensors, for example, or you can do it with a force platform if you're just doing an initial experiment, and then use that to drive the response, the joint level response of the exo. And what's cool about this is that you can recover. So far, we've just tuned the model. We haven't deployed it on an exo yet, but you can recover the joint level torque response at all three joints only from the center of mass state. So it's kind of a one to many, right? It gives you this really nice platform for multi-joint control. Okay. What about walking, right? So that was platform standing. Benny Liestma, she's now at Harvard doing a postdoc, was in the lab for 4 years and programmed this Karen system. So this is the rug pull experiment, but now it's in the context of walking. So that treadmill is on a big, what we call Stewart platform. It's got 6 motors that can throw the platform around, kind of around a half sphere, so you can actually tilt it too. We haven't done anything tilt yet. It's just, now we have a rug that can come from any direction at any time. We time it to the gait cycle, and we can change the magnitude that we give. So it gives us really nice like variable data set, which now we're going to throw machine learning tools at this. Okay, so we're going to get a lot of data from a lot of individuals almost falling in harness. And we think we're being comprehensive, right? Because these are coming from all directions and all timings. And what we're going to do is measure some state variable. We've chosen angular momentum as our measurement of choice, mainly because there's a literature about angular momentum and balance. There are many other things you could choose here. The bottom line is that something is steady, a perturbation comes, it goes unsteady, and it returns to steady again. And you want to measure how fast that takes. How fast does it take, or how long does it take to get back steady again? That's one way to think about measuring balance, right? And Jenny was really interested in whether whole body angular momentum could be an indicator of imbalance. I don't have time to get into this. Go read, there's a really cool paper in JAB on this that's from 2023. We classified all the behavioral outputs, whether a person jumped, how severe their perturbation response was to different directions. And you can kind of classify into jumps, which are really disruptive, and then small to large unstable responses. The jump, I'll just say a little bit about that one because it's super interesting. Take a moment to think about which direction should the rug pitch you to make it really hard for you to recover, and at what point during your gait. So the beginning of the gait would be right here. Both of my feet are on the ground, and I'm about to take this push leg into a step. So it's snapshot is here. I'm at the middle of double support, early single support, mid single support, about to hit the ground again with that foot. Those are the times you can think about. And then I'm going to get pitched in any omnidirection. Which one's the hardest? Which one makes you jump? Early? Okay, some votes for early. Mid stance backwards. Anyway, it's not easy to think about is the point. We're going to get arguments for all the possibilities. The one that's really the toughest is right before you're going to hit the ground, because you don't have time to put this foot anywhere, and it comes from back here. So now if I were going to use this foot, I have to throw it back there. So the most agile participants do this. It's super cool, and it's like stereotypical. And not everybody does it, but people who do it get it. Like they become a pogo stick. Anyways, what you find is you can, through that protocol, you can really push the angular momentum in the sagittal and frontal plane, which we loved because we're going to try and learn from this data, right? So you can see this is color-coded. Depending on the timing and direction, I can get any old angular momentum trajectory, which is what we were trying to achieve. Another thing is we could mine those data to figure out which of the, whether the angular momentum was related to where people put their feet. And the answer is yes, there's a high R squared when you're in double stance. So you have a lot of time now to put this foot right. Not here where you don't have any time. There's a high correlation between the angular momentum that you take in that pose and where you end up putting your foot. So that might be a trick for control. And really what Jenny is trying to do, well, she's done this. We don't have solid results on it yet. She's writing it up. Her idea was to take those data, and then here's the wearable sensor data, and we're going to learn. People do that with a wearable sensing suit on, and then we can map the IMUs that are on their body. So we basically turn them into an instrumented satellite. We got IMUs on their feet, shanks, thighs, and their trunk. And we can relate those IMUs to the ground truth foot placement or even the joint moments, right? So what we're trying to do is take wearable sensor network to exoskeleton moments so that these fancy pants here that she created, which can do forward kicks, but also sideways kicks, can play through, and this is the coolest part, I think, the anticipated. So we can ask the machine learning algorithm to learn the future. So we can kind of speed up the control. It would be like a lead or lag compensation approach in controls engineering, but we're using data to understand where the joint moments were for people 100 milliseconds later. And then what we want to do is pull that now. So we're going to take the human delay and bring it to now in the exo. That's the idea.
The exo knows when the perturbation's happening.
In this case, we have a perturbation detector, which we also trained from data. It's only about 60% reliable right now, I'll say. But that's doing the triggering. So you could have an end-to-end system. Yep. Okay, I think I'm already an hour. I'm going to stop. I'm going to go all the way. I had a stroke mini story too, which Dave ranked, but I don't have time for it. So I'm going to go. I want to leave some kind of, I've been trying to do this in my talks, like things that I've learned from my students. I'd like to leave those things up. And you can take a look at those and we'll end and we can hopefully do some questions. Thanks. Oh, we can do the stroke story then.
So maybe just
All good. Next time.
discussion
Manny?
Yeah, so in the combo hip and ankle exoskeleton story, you showed that as the ankles, let's say, activation decreased, metabolic cost increased. So it was not intuitive, right? I'm wondering if the difference between what's happening at the hip and what's happening at the ankle partially can be explained by disruption of the use of series elastic element at the ankle, which isn't really a problem at the hip. And so if you're turning down your activation, maybe you're not engaging the elastic elements.
Yeah, it's a great idea, right? There's no potential to yeah. Yeah, so Manny Azizi asked whether or not part of the challenge at the distal joints, really, or any joint where there's a prominent tendon and there's a lot of compliance, is that those things tend to be exquisitely tuned, right, for certain behaviors. When you slap the exo on there, you mess that up. Person at best would have to relearn how to do that thing. And proximal architecture, where the tendons are very stiff and shorter, you don't have sort of these tuned mechanisms in the way. You can just direct drive, right? Motor on motor. And I think that's right. I mean, one other thing I'll say anecdotally is we also know for every joule of mechanical work that we transfer from the device to the person, we save more metabolic energy at the hip. Like, that's a thing. I'm not going to say it's fundamental, but it pretty much is true. And that's because that thing was already less efficient to begin with, right? So if you're trading mechanical work onto a joint that may be relying on elasticity, there's not an opportunity there to save as much as when you're just
for the savings.
Yeah, it's straight work to muscle work at the direct drive joints. So there's a lot of reasons why I'm kind of all in on hips right now. Also, for the balance problem, like putting ankle weights on someone and then trying to improve their balance, not so sure. And the foot placement is really a critical element of that. And that's all driven by hip muscles in both planes. So, Monica.
You think you could maybe think about doing a hybrid where you have assistance at the hip, you're doing resistance training at the ankle. So you kind of like are improving the function.
For sure. Yeah, I mean, I imagine the phone app where like I could see like all three joints, and I have like I can choose agility, stability, or economy mode. So I'm like, I need agility mode. I'm about to try to slam dunk or something. And then I'm like, either it knows that it just has to power my hips because that's right? Or I'm like, engage these joints in this task. Well, that's kind of, like we think about it that way for sure. And then different solutions for different things. And then can you wear it all at the same time? No, not yet. Like, you wouldn't want to have all three of those on, but humanoids can do this stuff. Humanoids is an interesting place to think about playing with that. Like, we call it the trifecta in my lab, like the three kind of arenas of performance. Like, if you want to make a humanoid go in agile mode, human biomechanics can tell us, we should like overpower the hips or something, right? So, only professor questions? Come on.
I'm still figuring out how to relate this question, but it seems like sort of in the exoskeleton world right now, it's a lot of like single plane of motion.
Yeah.
When you give someone an exoskeleton like that and their body sort of readjusts to that, what do you lose as far as like our bodies have more degrees of freedom than that in order to have the stability and how do you get to the next level of still savings while retaining that?
Yeah, that's a great question. I mean, I think that's a whole area of the field that's underappreciated, which is like, how does the thing fit in such a way to not disrupt the normal degrees of freedom around your joints? And we're not good at it, especially with rigid robots, right? Like you noted, like even in the fancy pants hip that has we had to explicitly put 2 degrees of freedom in there because we knew that frontal plane is typically the most unstable. So if you only had a straight ahead sagittal exo, you're not solving the actual problem, which is I need to get my foot out. And you might also be preventing people from getting their foot out, which I think was part of your point. So, I mean, the simple answer is we have to consider more than just 1 degree of freedom, especially as the performance range becomes more unsteady and maneuverable and agile and stuff like that. And that's where folks who are good at textiles engineering and thinking about the interface and smart materials is another kind of opportunity there. We're not there yet.
So it's really good with the eversion, inversion added and a TA kind of actuator added in as well. So the ankle is not locked into
yeah, but then the trade-off is now I need like more actuated degrees of freedom. And how do I deal with, can I do an under-actuated like tensegrity system? Or it's not like the human body is awesome. It's not just humans, like animals, they got it. Yeah. Okay.
Are there plans for doing these sorts of experiments with populations with high and asymmetric muscle tone, such as stroke patients?
Yeah, so I have, okay. Thanks for asking that. The answer is yes, we have. I'll tell you what the solution is so far. Hips, sagittal plane, this is not for balance. This is just improving mechanical, neural, and metabolic effort in tasks of daily living. So we also did things like sit to stand, going upstairs, Tai Chi actually, because we're thinking about making sure these devices can be used in a rehab setting. So here's the strategy. We collected a lot, just like we collected a lot of data in the rug slides, brought 20 stroke patients in and we collected their biomechanics while they did activities of daily living. And we turned that into something like a foundational model, like think about an LLM for language, but now you have a model for movement, in particular for people who have impairment. You use that model to map what the mechanical intent of the person is from their wearable sensing suit. And you drive a hip exoskeleton in this case with those signals, and you can get between 10 and 15% mechanical effort reductions across those tasks, right? I mean, people haven't taken it home yet, but they come into the lab and we have them repeat the same activities of daily living. Again, this includes sit to stand. They have to walk over an obstacle. We do turning. Actually, we have one where they have to throw a medicine ball. And so the play here is like heavily data-driven foundation model for movement that you extract the control for the exo from. And it seems to work okay so far. So, yep.
I'm kind of wondering how close that maps onto with someone that has balance issues, because
yeah,
I'm disabled. I do have balance issues, and like what I experience is more of like a slow, gradual shift in how I move.
Yes.
And so I'm not really sure how well that maps. Like how well.
Yeah, I think you're right. It's totally hear you. These are probably not the best representations of most of what happens in the real world when people fall. But it's convenient because it's highly measurable and instrumentable, right? And we can still get insights, I think. How are we addressing that gap? One way is you guys have the bumpum here. When I say bumpum, I see a lot of, do you know what the bumpum is? You haven't seen it? Okay, so bumpum is I wear a rock climbing harness and I have Spider-Man cables coming out in all directions and they're like attached to the treadmill rail. And I can press buttons to pull at any rate from any direction, but this time on the trunk. So it'd be more, that's why it's called bumpum. It would be more, even though this is it's more like pull'em. But the idea is it's driven by the notion that a lot of people fall because they get bumped unexpectedly, right? Like that is it's not an uncommon falls mechanism. And it's usually, it can be slow. The other thing is that sometimes people fall without getting touched by the environment. They just didn't get the right signal to their muscle, or they were distracted by their phone or something, right? So, I mean, these are all, you would want to, the foundation model for balance, just to keep on that analogy, would need to include all of these modes of disruption. Like you get people in the lab on their cell phone, right? Or even better, like if the wearable clothing first only had sensors but not actuators, and people were willing to take it home, and you could label those behaviors to train models against any behavior, that would be pretty rad, right? So that's where we're headed. Like foundation models for language are going to start being applied to movement, I think. Dave.
Yeah. So there's like hundreds or thousands of papers on like motor adaptation. So you apply forces to people and they adapt, and that's been like modeled like crazy.
Yep.
And then, but how does that apply to?
Oh
So
man.
you're applying forces to people. It seems like those would just be perfect to apply for predicting how people are going to respond. But I don't see that link made very often. Or
Yeah, it's not yet. I mean, Sasha, who's in the back row, is working on this, right? I think you know her work.
Yeah.
We're just to the point now where serious motor adaptation experiments are being done with wearable robots in the legs. Yeah. So like LUM's work, there's some swing phase robots where we know a little bit about motor learning and so forth. As you know, like that literature, most of those papers are upper limb historically.
Yeah.
Then there's the whole split belt treadmill corner of the literature, right? Where you have people walk and the belts go at different speeds and they have to adapt to that. I think of the exoskeleton as it's a force, it's on your body, you have to adapt to it. Why are we not applying the same kinds of motor learning principles to exos so that a performance metric that we care about is how fast someone learns it, right? So we are starting to do some of that, thanks to Lena Ting, who's interested in motor adaptation in that standing balance paradigm. So we're trying to take some of those tools into learning to walk with an exoskeleton, which will involve some EEG measurements, and so is it cortical versus peripheral, feed forward versus feedback, all these things that I of course about. Like you wrote a lot of those papers. Yeah. You wrote 1,000 of the 20,000 or something.
So it's pretty cool. Like for numbers for me, you have like
task goal is well defined.
Update laws that could apply. Like I'm thinking like David Franklin and Etienne Burdett. And like it seems like when you apply those to muscles during gait, it doesn't.
I don't know. Like if you look at the center of mass mechanics, I was just talking to Sasha about this yesterday. I think if you pick a global variable that's a decent representation of the state, you can see first order learning curves that look like the classics. You see it in energy cost also, actually. Metabolic rate looks like canonical learning in an exoskeleton.
But how long? What's the time?
Very long. Well, I don't know what's long to you. It's hundreds of hours if you let it go to real steady. Yeah, exactly. Like 30-minute window. Well, okay. So it's about a step per second over 30 minutes. Yeah. So do the math. 30 times 60 times 60. Or how many 60s are in there? 30 times 60. I'm on the spot. It's a quals exam. Okay, thanks, man. So it's not a lot of repetitions, really, right? If you think about how many of those you took since childhood, if you think of a step.
Yeah, but all the force field stuff is like, it's more like 10 or 20.
So you see very rapid things. You see multiple time scales also, just like in the upper limb. Yeah, and the cascade goes with like if depending on which aspect of the physiology you observe, the rates are different, right? So like EMG tends to be, help me out on this, Sasha, I might mix it up. If you look at kinematics versus the EMG versus energy costs, I know energy costs is the slowest. That's like a fine tuning event. right? It's like I have some objective. I need to make sure I don't fall over. Good. Change my policy to solve that part. Now I'm just going to like infinitely search for an energy well. And that can take hundreds of hours, right? There's this really nice 3-participant study, again from Steve Collins's lab by Katie Poggenzy that you should look at. And she went long. That's why there's only 3. You know, typically we'll do 10 or 12, but they were like, let's double down on the longitudinal. Yeah. So maybe it's not 200 hours. It's 200 minutes. Yeah, minutes. Thank you. And most of the good stuff's happening in the first 30 minutes. That's true. They also showed that, again, this is the sort of signature in the motor learning and rehab world, like there's some retention. So you leave, you go away for 40 hours, come back. You don't start at the beginning. You kind of, you're not where you were, but you can tether together these sort of first order things. So there's continual learning that doesn't have to be online is the point. Maybe that's not the right way to say it, but you can do it not during one 200-minute session, right? Like learning any task, I guess. Yeah.
I have a question that relates to that. Do you have any studies where you're actually trying to put exos out on people over long periods of time? So that you can see how. Yeah,
we don't have any. We're trying to play the split belt treadmill game with exos now. So that those would be like 30-minute. Is that what you mean? The hypershell, you could do it. We don't. I mean yeah, that's what Jordan really wanted to do that with exos, and then COVID hit also. So like she got smashed by bad timing a little bit. We don't, but I would love to. The hypershell is the one that I would probably do it with, which is the hip exo. The annoying thing about that is they won't let you jailbreak it. So like I don't know what the controller does. So I know that it's supposed to do this.
So we need open source tools for.
Yeah, an open source tool would be nice. University of Michigan has a good open source exo that they're working on. But yeah, graduate students in the room, like that is, if I were your advisor, I'd be okay with 3 subjects over the next 5 years. 1 paper. Yeah.
I just had a question about kind of the power source used to power the exoskeleton. So I assume that you need like kind of a lot of power in order to use it. And like, what is your solution to like heavy battery packs that you might need?
Yeah, great question. Right now we're in a pretty good place because the motors we use are from drones. So I didn't talk a lot about the hardware, but we buy, the company's called Cube Mars, and these are, you know, they're basically the size of a donut, and they go straight in collinear with the joint, and the amount of battery power they need is reasonable. So people carry around something like a small Ryobi drill battery. We actually use Ryobi drill batteries because they're easy to recharge, right? You can just be like, and they're not super light. I mean, there's definitely room to innovate here. But you know, like in that stroke stuff that I just described by words that I didn't get to the slides on, over that 3-hour session, like we've only used 1/4 of the battery, and they're pretty much continuously using it. And they're doing like reasonably high powered things. So yeah.
Do you think the commercial solutions will use regenerative?
Oh, I hope so. Yeah, I mean, it remains to be seen like how much regenerative energy there is available. So far what we know from the literature is from, it's actually kind of funny because it's from the cases that I don't think are the best ones we should be exploiting, like going downhill, for example, where the leg is definitely absorbing energy and muscles are generating heat. I don't know of any study in the literature that's examined how much energy you can harvest from going downhill. Like, where is that study? Someone should do that one. Yeah, it's a win-win, right? So you basically have a generator on the legs, and that works for level ground-ish. Like there's a paper from 2008 by Max Donnellan that showed this, that it's possible. But the amounts of energy are enough to maybe like keep your headlamp or your cell phone alive for one call where like the rescue team's going to come and get you, right? Not much, but I think though they weren't studying the right conditions is one point I'd like to say. Yeah, downhill or, and they also showed that you could put it in like a mode where you're willing to spend a lot to get the energy. So, like these hand things that you're like, oh, I know I'm going to like burn out my forearm muscle, but I really need this power.
Yeah.
We could do that in Exos too, where you're like willing to trade the energy for the energy. There needs to be more experiments in this area for sure.
Lisa's raising her hand.
Okay. Hey, Kisa.
Hey, Greg, great talk. Yeah, so I was just wanting to say that, I've been reading a lot of old papers and there's some new papers and, going back to like 1964, people have shown that, muscles can store up to like 60% of the energy. Oh,
Kisa,
yeah, you're
I'm
not,
going to repeat your question after you say it because we don't have a loud enough mic in the
okay.
room.
Okay, well, I'll make it really simple. So yeah, it seems like muscles can store up to 60% of the energy expended in stretching them. And this is like the basis for the stretch shortening cycle effect. So I just wanted to just say that I think that those studies, and Natalie Holt has a paper on this too, suggest that there is really like substantial energy that could be, regenerated and, even
That's actually in the muscle, not just
yeah.
the plastic
Yeah.
elements. Okay, so let me try to quickly recapitulate. Kisa brought up the point, which is that the bar charts I showed that had muscle and tendon, you can also break the muscle bar into elastic energy storage further, right? So that we know that there are protein springs in the muscle proteins that are also capable of storing and returning energy. And that's not insignificant. Kisa mentioned that can be 50 or 60% energy returned actually from that fascicle bin at springs that are at lower level of musculoskeletal organization. And we shouldn't forget about those. And I agree. Okay, probably got to wrap up, yeah? All right, thanks all.